तो आज का टॉपिक क्या है?
फ्रैक्चर across the surface इस पॉइंट पे उसका माइक्रोस्ट्रक्चर कैसे वॉइस वगैरह बन गया।
Yeah. So it is called Fractography, and we will study qualitative, but the main focus is quantitative fractography. Okay. So whatever we do with the K1C, J1C and parameters like that, they will tell before using the component that this material you should use and this should be the dimension of the material based on the design parameters you should use. Fractography is something which is post-mortem of the material. Okay. So whatever we do, components will fail. Even if they are in design criteria, sometimes they will fail. And we have seen a lot of accidents where human lives are involved and sometimes not. But accidents cannot be avoided. Can it be avoided? So you think if you are driving a car, can you avoid an accident? Yes?
Being very careful.
Yeah? No. You can't. You can control yourself, but you cannot control the environment. Okay? So accident cannot be avoided. Unless all the cars are on autopilot mode. So all of them are Tesla and controls are taken away from humans. Only then accidents can be minimized to machine error. कि अचानक से इंटरनेट उड़ गया, फिर सारी कार्स आपस में भिड़ गई, वो हो सकता है. Okay, but as long as human intuition, indulgence is involved, accident will happen. Okay. So similarly, when components fail, then people want to know why it has failed. So we have invested a lot of money and research in making power plants and bridges and reactor pressure vessels, ships, aircraft, but even then they fail. Okay, and very recently you have seen Boeing accidents. So when they are failing, then how do you know why they are failing? So you look at the component, and then the failure will leave some signature. So it's like finding out the murderer, why the murder has happened. So that is what fractography is. Okay. So once we have a failed component, so in order to understand why a component has failed, you need to systematically understand what happens when a material fails. Okay. So what are the signatures at the fracture surface? Okay. So it is analogous to, in order to understand the murder which has happened, you need to do a lot of necrophilic studies. So you need to do a lot of autopsy on bodies, and you have to understand that if a bullet has hit, how the wound would be, or things like that. Okay, so in that case, people don't deliberately do killings and look at the forensic signatures, but in fracture case, you deliberately break samples, okay, and then you look at the features, and that's how this field has developed. And then we can, and so the real scenarios are not really that easy. Okay, real scenarios are really like a murder mystery. That you look at the component, it will not tell you the right signature. Sometimes it will be a combination of a lot of features, and then you cannot find out what really is happening. So it needs experience also. Okay, there is one story, where I don't really remember the references now, but military aircraft which was in the war was analyzed for the area where they were damaged, and then they looked at the area, the component where maximum damage has happened during war, and they designed a new one, and all of them were also compromised. Why? Because they could analyze only those aircrafts who came back from the war, right? And those who came back from the war, they survived. So the maximum damage area was really not the maximum damage area because they survived, right? Right. So that kind of experience is needed to understand what is happening. So in this slide, you see that at what scale, which kind of for observation you need to observe, right? You need to see. So at 1x, you see from your eyes, and the resolution of your eyes. How much is the resolution of human eye? Yes.
Resolution is
25. What? Centimeter.
No.
25.
Both the length, the range of the human length.
Human eye का resolution क्या होता है? What is the resolution?
दो nearest object को distance.
Yes. So then tell. Characterization नहीं पढ़ा है तुम लोगों ने? नहीं पढ़ा है?
What around
0.1, 0.2. 0.1 to 0.2 millimeter is human eye resolution. Beyond that, you cannot distinguish two lines. It will appear that they are merged. They are one line. Okay. And then with a hand lens, buy it in Amazon and it works at 10x. Okay. Then a stereo microscope, 100x. Optical microscope, 100 to 1000x. Scanning electron works from 10 to 10,000x, 20,000x. And transmission works at a very high level. But it doesn't mean the best one is transmission electron microscope. It doesn't mean that. Okay? You will see different features at different scales. It will not be the same features. Okay? So it has to be, sometimes it has to be a combination of characterization at different scales to understand what really has happened. Okay? So then let us look at the features which are there. So we have unit cells, we have substitute. So atomic scale, you want to look at, then you can look at the substitutional atoms, interstitial atoms. Then you see this is an edge dislocation here, and this is an screw dislocation. Okay? And then you can see a feature like intergranular fracture. So the fracture has happened along the grain boundary. Okay, and then you can see transgranular fracture. Okay, and in order to know if it is a transgranular or intergranular, you should also be able to see the grain boundaries. Okay, so you will need to etch it. Otherwise, you will not find out if it is intergranular or transgranular. Then you can, at different scale, you can see precipitate, whether or not they are incoherent or semi-coherent. And you can also see the grain boundary precipitate. Sometimes they are of this type, sometimes they are in the layer form. Okay. And then these are slip lines or slip bands. Okay. So we have not studied in details how to observe dislocations. There are different ways of looking at dislocations. So one way is microscopy, then there are indirect ways where, so Kikuchi pattern and things like that, there from those you can find out how to see the dislocations. And then let us also look at different scales. So electron cloud and all those things are at 10 to the minus 6 millimeter. And then you have dislocations which are in the range of 10 to the power minus 5 millimeter. 10 to the power minus 5 is how much? 10 to the power minus 2 micron. 10 to the power minus 2 micron is 10 nanometer. Right? Or not? Yeah? And then you have subgrain boundaries, 10 to the power minus 4 millimeter. So that is 0.1 micron. Then subgrain slip bands, 10 to the power minus 3, so micron levels. And grain inclusion, voids, elastic plastic field is in the range of 1 millimeter. Large plastic strain is in the range of 0.1 millimeter. Stress intensity factor is in the range of 10 millimeter. because you want to keep the plastic zone small. Okay, so that line is a plastic zone, so that one is there. And specimen or component is in the range of 100 millimeter. Okay. Now, what happens when we, so this is an example of ductile fracture. The material is ductile, so then you load it in tension, in shear, and in tensile tearing, and in all those cases the voids will form in this way. They are all different, right? So in mode 1 the voids are opening like this, in shear they are opening like that, okay? And when you break them, then when you look at the features, they will look rough, okay? They will look rough, and when you look at it under scanning electron microscope, then you will see dimples. And that's the signature of ductile fracture. Whenever you see dimples you cannot see from optical microscope, or from naked eye, of course you can't see that. But from naked eye you can see roughness, and roughness is a measurement of ductile fracture. What do we want to achieve from quantitative fractography is, can we relate these features quantitatively to the materials parameter, and this also helps in reverse engineering. Okay, it also works in retrofitting or what do you call it, archaeological studies. So when you have very ancient things and then you look at the fracture surface and you want to know what has happened, really not alone this technology will not work, but you will have to combine this with many other studies. Okay, so dimples will be oriented in different directions, and that depends on type of loading. It also depends on type of treatment you have given to the material. So I can get this kind of dimple in this situation also. In the upper one also I can get dimples like that. How? If my plate is rolled in one direction, then I will get dimples oriented in one direction. Okay, so that is the confusion. That is where experience counts. So you look at this and then you are thinking this has happened, but it could also mean that a rolled plate has broken. Okay. And the average of dimple size, when you look at it under microscope, so like you calculate the average grain size, similarly you can calculate average dimple size, and that average dimple size can be related to the fracture toughness. Why? Because damage kinetics depends on material property. Okay, so if a dimple is growing, when this will achieve, so it is achieving some value of diameter at any point of loading. When it will break, that is decided by material's behavior to accommodate how much strain it can take. Okay, so that will tell how big of a void you need to make it critical, right? So if the material is very ductile, then you will have larger dimple size, but then it is not that simple. Okay, because the kinetics of void is nucleation and then growth and then coalescence. Okay, so nucleation, growth and coalescence, this is the mechanism of ductile fracture. So if the material is strain hardening, more strain hardening, okay, so it can take a lot of, so if the material is something like this, not much of a hardening, but it can accommodate a lot of strain. Okay, so it has a lot of slip systems and stacking fault energy is good enough so that cross slip can happen. Okay, and so dislocations are not feeling much barrier, so strain is accommodated by the deformation. Okay, so in that case what will happen when damage initiates, you will have the nucleation at whatever grain boundary. So nucleation sites are not manifested by materials deformation capability, but it is manifested by the grain size and things like that. So how the design of the material is inside, and when I say design, not mechanical design, design meaning how the microstructure is. Okay, so how many precipitates you have and secondary phases you have. On those, it depends that where and how many nucleation will happen whenever it happens. Okay, so nucleation site is not controlled by material deformation property, but growth is. Okay, so if the material can accommodate a lot of strain, then all of those will be growing not to a very large size. Okay, they will be growing slowly, but matrix is able to take a lot of load and they will not break. Okay, none of them will break. They will have to achieve a very high diameter in order to fail. Okay, but if the material is strain hardening, then you need to increase the stress for every increment in strain, and that will cause more hydrostatic stress, also shear stress. Okay, so that will cause more growth in the dimples, in the voids. Okay, and they will coalesce, right? And so the average diameter in this case will be smaller than in this case. Okay.
Only for loading. Why sir size is less and
What?
why size is less? Dimple size is less, sir.
In which case?
In lower when the lower the stresses.
Dimple size is less because the matrix is able to accommodate more strain. So you are supplying some energy, right?
Okay.
You are giving some mechanical energy. Okay. And that mechanical energy is consumed in making the voids and growing it, right? The nucleation and growth. And the energy which is being absorbed as strain energy.
Okay.
Right? So if the material is able to take more strain, then maximum amount of energy will be going in strain form.
Huh?
Right? So plastic dissipation will be more, and not much energy will be available for the dimples to grow, for the voids to
Formation
grow.
of growth.
Okay?
Okay.
Voids can grow only when the matrix is resisting.
So, but in case, sir, when the strain is high,
Yeah.
in lower case.
Strain is high. In
Yes.
lower case.
Strain is high. So maximum energy goes in a strain formation. So
Strain
energy is less. So dimple size is less in
Yes.
this case.
Yes. Dimple size will be smaller in this case.
It
But
means
when they fail, when will they fail?
it's fail
When it becomes critical.
critical.
And what size of dimple will become critical? Smaller size will not be critical for them.
Yeah.
Smaller size of dimple will not be creating a scenario where a crack can initiate. You will need a very large dimple size, very large void, so that it becomes critical. Okay. So what is critical crack length? If you look at it with the stress intensity factor, then from that you can, although in a very highly plastic material you shouldn't take K1C, but just for the sake of it, if you calculate this for any given amount of stress, A will be larger if this is larger,
Yes, sir.
and for ductile material, for this one K1C will be more, or for this one K1C will be more.
Yes, sir. नीचे वाले का.
नीचे वाले तो K1C बड़ा है तो A बड़ा होगा.
हाँ.
So you will need a very high crack, very large crack, so that fracture can happen. That means the void has to increase in a very large amount of diameter, so that it can achieve that critical crack.
Okay.
But the kinetics is very different. So if you have more number of nucleation happening, then it may happen that not all of them will grow to a larger size. Okay.
Sir, any factor of time is here, because if strain is more, then it will take more time to deform.
Well, we don't say anything in terms of time, because we are not talking about time dependent deformation. So in this
No.
case, kinetics is in the terms of plastic strain. Plastic strain develops with time only. Okay, but we are not saying time because then it will make it time dependent.
But sir, when stress is high, it will take less time to deform. Finally,
It will
plas-
take, when stress is high,
High.
it will take less time to deform, meaning
It means less plastic strain is there.
for the lower case,
Upper case, sir.
for the upper case, what will happen?
Strain is here is strain is less.
It doesn't matter. So if you look at the kinetics of damage,
Yeah.
then what is defining nucleation rate? So let us take GTL. Okay. So nucleation rate is defined by how much meses is there and how much plastic strain rate is there. Okay. So the stress is higher, that will matter, but you have same amount of plastic strain
Okay.
at that point. Okay. So then that is also governed by the plastic strain, how much that is. Okay.
Okay.
So this is what I was talking about. So initially you will have void formation. This is a schematic and real scenario. Okay. So what is happening in real scenario is that you have void everywhere in the neck region. Okay. So locally the stress has increased to a very high value, and plastic strain is different at every point. So that's why you have different amount of void size at every location. Okay. And highest amount of stress is probably here, and also constraint is very high here. So a lot of voids has actually coalesced. Here also coalesce has happened. Here also, here also, here also, here also. And you also see a trend in shear direction. Right? This thing has also opened in shear. Okay, so von Mises is playing a role there. Okay? And not these coalesced voids. So here also you have coalescence, and they are not critical in size enough so that they lead to fracture. Okay? So if you take a piece of paper, which we have a lot of them, it's a question paper from 2022, so we can use it. Okay? So So it's good that we have only 2 students in class. Okay. And then I create. And then in this case also I create. You want 2 cracks, 3 cracks? How many cracks you want? 3 cracks. Now you tell me, when you pull it, how many cracks, how many pieces you will break into? One piece.
2 pieces.
You will break it in 3. Try and break it in 3. You can try again. Maybe it was your bad luck. You can create more cracks. You can create very damaging cracks also. You can do that also. How many pieces are you breaking into? 2 only. Why not 3? Why not 4? Have you seen anything break into many pieces at one point? You have.
Yes.
Yes. Shattering of glasses. That can happen. But in this case, what is happening? Why it is not breaking into more than 1 pieces?
So because we are supplying energy,
Mhm.
and sir, that energy is being taken by one crack. And what happens in brittle materials?
Forget about bitter material. In this case, why you are not able to create more than 2 pieces?
So because rate of growth of this void is not
Void?
So means this crack is not that much fast that it can so it can accommodate that energy which we are supplying.
Fine.
And
So why both cracks are not propagating?
Sir, stress concentration is there.
Yeah, I created both cracks, two cracks of same size.
Yes.
So stress concentration will be same on both. No,
Same on both.
you create two cracks of the same size.
Sir.
So one of them ought to be different by whatever means you make. Okay. We are not making two photons. Okay. So whatever crack you make naturally or by your own hands artificially, they are going to be a little different from each other, and the matrix around them is also going to be a little different. Even if I create hypothetically two exactly same crack in the material surrounding that crack is going to be a little different. Okay, so one of them will take the lead, and whoever takes the lead will always have the lead, right? So जिधर भी जैसे नेकिंग क्यों हुआ, नेकिंग कहीं भी हो सकता था, but if it is the necking started here, the stress has increased here and it will keep on increasing there. Okay, so once initiated, the system will support the formation of that. Okay, so once a coalescence cluster becomes critical, the crack takes the lead there and all the other things will stop. Okay, and this will start propagating, and in their direction it will cut through all the voids. It's like you have that notepad where you have dots. Okay, so the crack will connect with all of them, and then when you look at it you will see this roughness. Okay, so this roughness becomes a feature of ductile fracture, and the roughness will be more when it will be more if the dimple size is more, right? So when two dimples, so between two voids you have a material which is connected, right? And that connected material acts like a tensile specimen. So if I have two voids which are very close to each other, then this part is connected and this is like a tensile specimen, right? And then it will stretch, so it will get thinner and thinner. What does that mean? How it will get thinner? Because the two voids are increasing. That's how it is stretching. Okay, and then it will break. So as much it can thin, that much roughness you will have, right? So that's a representation of ductility of the material. Okay, and this roughness you can measure by different means. Okay, what means you can use to measure roughness? How do you measure roughness? बोलो बोलो, रफनेस मीटर का नाम नहीं सुना है? नहीं सुना है? So you have a probe, a stylus kind of thing which moves through the surface, okay, and then it notes down how many valleys and crests it has passed through, how much depth it has gone through, and it calculates an average of that, okay, and that is a roughness value. Apart from that, you can also use a laser profilometer which will scan the upper surface, okay, and it will tell you the elevation. So it will exactly give you the coordinates, XYZ coordinates of the mountains, so crest and valleys, and from that you can calculate an average roughness value. So if you have something like this, then this is your roughness. Okay. Apart from that, then there is something which is very unique, and that is a tree or a broccoli. Have you seen a broccoli or a cauliflower? I am now trying to draw it and I will fail. So this is broccoli or cauliflower, whatever it is. Yeah. So this is how it looks like, and then you take this piece out and you look at that. That will also look like that. A small piece looks like that. Then you take one piece and that also looks like that. Okay? But if you cut here, then that will not look like the whole thing. Okay? And if you have heard of golden ratio or golden spiral, which follows Fibonacci series, okay, then that looks like this. And if I look here, then it looks like a golden spiral. If I look there, in here, it looks like a golden spiral. And if I look there, it looks like a golden spiral. Wherever I make the cut, I see the same thing. Right? Here, if I make selective cuts, then I see the same thing. This is called self-symmetry. Okay? Things are symmetrical. They need not follow Fibonacci series, but they are symmetrical in some way. So this is continuous symmetrical, this is discrete symmetrical. Okay? And so this is a signature of the whole design of this system. Okay? A tree, you take a small branch of that, it looks like that. Then you take a small piece of that, it looks like that. Okay? So that also has a representation of self-symmetry in it. Right? Similarly, at same condition, when the material fails, this material should also be showing some kind of symmetry. Okay? Because it is the same material. Okay? So the voids are going to coalesce and break at same conditions. Right? Because that's the property of material. So it is going to show the symmetry whenever it happens. Right? So this self-symmetry representation should also can also be related to the material property. Right? But counting this symmetry is tricky. Counting this symmetry depends on scale, because if it is not continuous symmetrical, then you need to define a scale. So if you have a coastal line, it is not a coast. Okay, so how is our country? Something like this, huh? Then what do we have here? Sikkim.
Yes, sir.
And then what do we have here? Arunachal Pradesh, something like this. Then we have Bengal, then Orissa. Then what do we have? Huh? Andhra, and then Tamil Nadu, then here Karnataka,
Yes.
Maharashtra, then
Gujarat, Rajasthan.
Gujarat, something like this. Then Rajasthan, ये थोड़ा बिगड़ गया इधर से, है ना? ऐसा कुछ तो भी है, ठीक है? So this is a coastal line. It looks like a line. Then you magnify it. Then the coastal line looks like this. Then you magnify that. It again looks like that. Then you magnify further, it will look like that. Okay, so it has self-symmetry. So how do you calculate the length of coastal line? If you determine the length of the coastal line by putting a scale of 1 kilometer. You put a scale of 1 kilometer, okay? So you put a scale on this zigzag line, which is of, let us say, this length. Okay? So this is 1 unit, then I put it here, 2 unit, then I 3 unit, okay, and 4, and 5, 6, 7, 8, 9, 10. Now I choose a smaller scale, which is half of it. Okay? So the length should be double of that. So the total length in number of units. So here I have 10 units. So here I should have 20 units? No. No, it will be more than that. Okay? Then I choose another and I will have different value. Okay? But this is capturing the roughness and there is a symmetry. Okay? So the concept tells that if you choose different scales and you calculate the total length, the log of that will fall on a straight line. So log of number of scales you have chosen and the size of the scale you have chosen, that should be a line, a straight line. And the slope of that represents the self-symmetry parameter, which is called fractal dimension. Okay? And fractal dimension is simply the idea that a smooth surface is a two-dimensional entity and a smooth volume is a three-dimensional entity. What is a rough surface? It's somewhere in between 2 and 3. A straight line in one dimension and a surface is 2 dimension. What is a zigzag line? It is somewhere in between a surface and a straight line. So it should have a dimension more than 1, less than 2. So it becomes a fractional dimension, and this is the idea of fractal dimension. Okay. So when you look at the scanning electron microscope of the fracture surfaces at different magnifications, okay, and at each magnification you take an image, okay, and that image will have dimples. So something like this. So this is how the dimples will look like. Okay, and then you divide this in small boxes, small pieces. Okay, and then you count the boundaries of the dimples by placing boxes around it. Okay, and then you do it for different magnifications, and then you plot them. Okay, and for one magnification also you can change the boxes, and then you can plot this, and then you get a value, and this value you should do it at different locations. Okay, and then you should see how the dimension is coming, if it is too much away from each other or the values are really giving a signature of the material. If they are really giving the signature of the material, then you have obtained the fractal dimension. That is also a measurement of roughness only in this case. Okay, and that has been tried to be correlated with the material property, and so far people have found absurd results. Okay, so they have found that it varies proportionally with the dimple size, it varies inversely with the dimple size, and some people found that it doesn't. It's not really, it can't be related. Okay, but it's a good idea to apply in this area, and theoretically or conceptually it has a physical significance and it should represent the material's behavior. Okay, so this is how ductile fracture will look like. So this is a dimple, this is a dimple, okay, and all of them are dimple, and white lines are the border where they have broken, and you see different sizes of dimples. This is a dimple, and inside also you see some lines. It means that that dimple has joined by other. Okay, so those are the boundaries of the other voids which were there before. Okay, so I believe the time is up, so we'll continue from here in the next class, which will be when? Monday.